Yeah, yeah.
We're good now? Yeah.
Yep.
Okay, everyone, I'm sorry for the delay. Welcome to the first AstroAI summer seminar. I am delighted to host Javier Roulet. Javier is originally from Argentina, like myself. I don't know that I needed to say that, but anyway, he was a student, a PhD student in Princeton with Matias Saldarriaga. Matias was here a while ago. He's a very famous cosmologist. After that, he went as a postdoc to KITP in Santa Barbara, and then to Caltech, where he's currently, and he's soon moving to Chicago for another postdoc. Javier has been working a lot on gravitational waves and also on applying machine learning or developing machine learning algorithms for gravitational waves. So I'm very much looking forward to the presentation. Thank you, Javier.
Interruptions are welcome, so if you have questions, just raise your hand, okay?
Thank you very much, Cecilia and Rafael, for having me. It's a great pleasure to be here. Thank all of you for attending. I will talk today about equivariant learning for simulation-based gravitational wave inference. So, yeah, just to a brief introduction about gravitational waves, so that all right. So, brief introduction about gravitational waves, so that we are all on the same page. So when we have two compact objects in a binary orbiting each other, such as black holes or neutron stars, that has a time-varying quadrupole moment, and this causes gravitational wave radiation to leave the system. This radiation takes away energy from the orbit, and then it makes the orbit shrink progressively. The more the orbit shrinks, the faster the orbit becomes, and the more intense the gravitational field. So the more gravitational waves are emitted, and this can be a runaway process that ends up with the merger of the binary into one final object. From our point of view, these gravitational waves that provoke this merger then travel across the universe, don't interact practically with anything, and reach Earth. The effect that gravitational waves have is to stretch and squeeze space-time by a tiny amount. So you can detect them with giant Michelson interferometers. So when a gravitational wave comes through, the arms of the interferometers get stretched and shrink, and then that changes the interference pattern at the output. And this is how we can detect these gravitational waves. There are currently three main detectors in operation, two known as LIGO in the United States, and one called Virgo in Italy. And then what the gravitational wave signals look like is this strain as a function of time. And the strain is basically by how much the space-time is being stretched and squeezed. And also, we can predict the detailed shape of this gravitational wave from the parameters of the mergers, such as the masses of the black holes and so on, using general relativity. And then, in turn, by measuring the detailed shape of the gravitational waves, we can infer what the parameters of the merger are. And this is what my talk will mainly be about. So what are these parameters of a binary system? It's not that many. It's two masses for the two objects. Imagine they are black holes. Each one has a spin, so that's three spin components. And then there's a bunch of extrinsic parameters, such a lot of angles describing the orientation of the system relative to Earth, as well as the distance and the time of arrival. So all in all, it's 15 parameters. And this completely describes the system, and these systems are very well measured because it's just pure general relativity vacuum. So compared to other astrophysical systems, this is very special problem for parameter inference because we really have a good hold on the modeling. So we are interested, why do we want fast and robust parameter inference? And this is where machine learning will come in. So one very clear application is for multi-messenger astrophysics. So imagine instead of two black holes, these at least contain one neutron star or potentially two neutron stars. Then there is matter in the system, and when they merge, can be diffraction and explosion, and then the electromagnetic counterpart. And then one can try to chase that with telescopes. So how this works is first the gravitational wave is detected from exactly the details of when each signal arrives at each detector and so on. We can estimate where it came from. And then point telescopes in that direction. So for this to work, we need really accurate and really fast parameter estimation. And we have some codes in place that do this. And in fact, there was a huge success story with GW17 or 817. If you know, that was a merging binary neutron star that was found in this way. But these methods currently do, the ones that are very fast, do some approximations, and then in some case, when they are followed up with more detailed methods, the sky location moves a bit, and then this can jeopardize these follow-up efforts. Then currently we have over 100 detections, but as detectors improve in the future, this will be increasing exponentially up to hundreds of thousands in the next decade. So as the catalogs grow, first of all, we need faster analysis methods, and also we are less tolerant to systematic effects, so we really need accurate measurements. And I should say also the approximations are not good enough because many of the interesting conclusions that we can extract from this system come from the detailed shape of the waveform and many subtle physical effects, such as spin misalignment or eccentricity or things like this. And then there's a potential other application that is not usually talked about, but that is for the detection. So using results of parameter estimation for detection, and hopefully I will talk a bit about this towards the end of the talk. But yeah, here when you're searching, you have millions of triggers, and then you really need to do this fast if you want to use this for searches. So a method that is relatively recent and is getting traction in the field is neural posterior estimation. And I will just briefly introduce it and also compare it to more classic methods like Markov chain Monte Carlo that you might have heard about. So in here, our goal will be to find the parameterized form of the posterior distribution. So here I'm calling theta are the physical parameters of the source, think mass is distance, d are the data, and p is the true posterior that we want to infer, and we do that by approximating it with some functional form that could be, for example, a normalizing flow or flow magic or other techniques. This distribution has many free parameters, for example, neural network, the weights of a neural network, which I'm noting with phi. And the idea is let's tune phi so that given the data, the Q will output the posterior distribution. It turns out this can be done by minimizing the KL divergence between the posterior and our target posterior. So it has the property, the KL divergence has the property that when it's minimized, the two distributions are equal. Furthermore, it can be estimated just with examples from the posterior distribution. So we can simulate millions and millions of signals where we know the truth, so we draw true parameters from prior, and we simulate data according to those parameters. This entails, once you generate a set of masses, for example, generate a signal, add noise to it as if it was a real detection. And those are your samples, and you can evaluate your model for the posterior on those samples, and this defines this function that turns out when you minimize it, Q becomes equal to P. So training only requires simulated data, and therefore it can be done upfront. So this training doesn't depend on any real observation. So you train the model before doing any real observation, and then when you take data, the model is already trained, and you get the posterior immediately.
Of course, that works if your simulation and the noise you add to it actually reproduces what you observe, correct?
Yes.
What happens if it doesn't?
So if it doesn't, then you have a problem, but you also have a problem in the usual method. For example, if you write a likelihood function and you run a sampler, and your likelihood function doesn't describe the noise process, then you are also in trouble. So then you are in a fundamental problem. So what this allows, so what this allows you, so you still need your model to correct your model to be correct to avoid bias. But a big difference from compared to more classical methods is that you never need to evaluate the posterior. Just need to simulate from it. And this is called simulation-based inference. And okay, all these properties make it very promising for these data analysis applications that I was talking about. And this, well, there are already some codes that do either this or similar methods that I'm listing here, but in this work, we'll try to improve the training speed by incorporating some domain knowledge. So why is gravitational inference hard? And this is mainly because the signal space is very large. So there are these waveforms that we detect have a very large number of possible shapes, a very number of different cycles, and so on. So for example, if you just vary the masses and spins, you already get 100,000 templates. This is, for example, the template bank that we use for searching for these signals, and that's the size of the template bank. So there are 10 to the 5 independent shapes. Just considering the intrinsic parameters and the extrinsic parameters like the distance, the time of arrival, and sky location, add more variability on top of this. So we certainly don't want the model to have to figure all this on its own. So to illustrate this, here is a catalog of the current detections that have been published. And you see that, so in each of these, the x-axis is time, the y-axis is frequency. And you see this characteristic chip-like feature that as time passes by, the frequency increases because the orbit becomes faster, and the amplitude usually increases too. And all these have very different time scales. So for example, in a neutron star merger, the signal stays for thousands of cycles in band. And a signal with 2000 cycles is different from the data point of view from a signal with 2001 cycles. So you really need a lot of shape to capture all this. But you also see that there is a lot of structure in these signals. So can we understand this and bake it into the model? And I will argue that we can explain most of this variability with a transformation group. So here, this is the most technical slide, I suppose, but we can do a simple analytical approximate model for what the signal is. And this will also help our intuition. So here, remember, theta are the physical parameters, and this is the waveform shape in the frequency domain. And it has some overall amplitude that depends on, first of all, how loud the signal intrinsically is. This is controlled mainly by the mass. How far away it is, which is controlled by the distance, and the response of the detector to that particular orientation. That's the amplitude. And then there is a phase term, and there is a constant phase, which is just the orbital phase of the binary. There's also a linear time frequency, which is the time of arrival of the signal, and this is again different at each detector because these waves travel at the speed of light, and the detectors are in different places. And then there are other parameters that control the shape of the signals, such as how many cycles are there in band. And again, this depends mainly on this chip mass of the binary, but there are other corrections where the other parameters like mass ratio and spins come in. Okay. And this structure can be simplified a lot if you just group all this thing into some amplitude and all these coefficients. They have the form of some coefficients that encode the values of the parameters and some phase functions that are fixed. And by writing like this, we see that under changes in these parameters, we can recover the new waveform from the old waveform with a very simple phase modulation or amplitude modulation. So this simple phenomenological model, which let me stress is not exact, it's just approximate, but it captures most of this variability in the signal space. So how can we use this to simplify the model's life? And I will discuss representations that try to respect these symmetries for the data and for the parameters, which are the two ingredients in the posterior. So first, let's do the data. And here the idea is we have these group parameters that describe approximately the signal, and we can fit them to the data. And so this step is not amortized. You have to do it after you get every piece of data, but it's not that expensive either. And this is because these parameters are very few. Some of them, like amplitudes and phases, are analytically maximizable. And another advantage that these parameters have a very clear physical meaning. We understand that this coefficient controls the length of the signal, this coefficient controls the amplitude, so they have a very clear meaning. And the idea is that this will capture most of the information that is in the signal, all the information that is captured by this simple model. And what is left should be the perturbations that we didn't include. Think effect of misaligned spins that make the orbit precise, or details like this that we still want to capture, by the way. So, how to capture them? Yes.
The input to the model is actually these parameters which are calculated from that original.
Yes, the input are both. So the parameters that we fit are part of the input, and the other one is the heterodyne data, which I'm about to describe. And this is basically whatever is not captured by the by the simple phenomenological model. Okay, in the jargon of the field, this is called heterodyning, but you can approximately think about it as divide the data by the approximate model. And if you remember the functional form that is like this, when you do that, the amplitude cancels, the phase cancels, and you're basically left with a constant. So to the extent that the phenomenological model is correct, then the heterodyne data has no information and is invariant to the parameters of the source. So if you get a signal that maybe a binary neutron star 2 minutes long with 2000 cycles, or a very short one, 10 orbits from a binary black hole, once you heterodyne the data, it will look the same. And this is illustration of this. So this is a real data. This is the tract of 17817, the binary neutron star. You can fit the reference model, do this heterodyning exercise, and this is what the data becomes. And if you are familiar with radio astronomy, this is kind of akin to the dispersion for the pulses, radio pulses. And yeah, the idea is that the heterodyne data is almost invariant to the parameters of the signal. what else? And yeah, but from the reference model and the heterogeneous data, you can reconstruct the original data. So in that sense, it preserves all the information that is not captured there. And another advantage is that now it's very easy to compress, because you can think either in the time domain, you crop a small window around this signal, and you translate a 2-minute long signal to a fraction of a second. Or equivalently, in the frequency domain, you can lower the resolution of the frequencies and downsample in this way. So, okay, this is for the data. And then, okay, both of these ingredients go to the model, so that's how the information gets conveyed. Now, for the physical parameters, how to represent them. And yeah, say here, gravitational wave posteriors are bananas. This is an example of a typical gravitational wave posterior. And indeed, you see there are many banana shapes, and yeah, there are many and have banana shape, and both of these things are bad for normalizing flow or something that tries to reconstruct this posterior. So how can we simplify the structure? And now let's step back for a moment from machine learning and try to incorporate our physical intuition to see how these bananas arise in the first place. And here, remember, this is the signal at each detector. The K is the detector, and it has some amplitude, overall phase, and overall time that are mostly controlled by the extrinsic parameters. And these quantities are very well measured, and this is how they control this measurement. So, for example, these bananas are constant, the contours of constant either amplitude or time or phase. So these are intuition, and then we have analytical expressions for this amplitude, phase, and time. So let's try to promote them to coordinates. So I will go quickly about this, but for example, the amplitude can be, so the distance can be traded for the amplitude. It has some complicated formula, but we know it, and it has a Jacobian that we can compute, so it's a perfectly good change of coordinates. And you see before you have these weird correlations, and after you do this change, the correlations are gone and the parameter is better measured. You can do similar thing for the time of arrival. Instead of using the time of arrival at Earth, which is not the center of the Earth, which is not constrained because we don't have a detector there, just use the time of arrival at the detector to characterize it. And indeed, this is much better measured and not correlated with anything else. And if you have more than one detector, this is the main way that we can constrain the sky location of the signal, because the time difference between the two arrivals basically defines a cone in the sky with a constant angle, so long as you, from a z-axis, which is the line joining the two detectors. So let's use that z-axis, and this is again what you have if you just use right ascension and declination without thinking about it. And if instead you use these coordinates that are oriented with the detectors, the posteriors become much simpler. Okay, similar thing we can do for the phase. Complicated before, simple after. Notice that here, for example, we still have, so it's uncorrelated and well measured, but still has two solutions. In this case, if you rotate the orbit by an angle of pi, the quadrupole moment stays the same, and this is the main thing controlling the gravitational wave. So you have a degeneracy there that is discrete. And similarly with the sky location here, we also have two solutions for every event. So yeah, all that I discussed so far is for removing the bananas and the degeneracies. How can we now remove the multimodality? And it turns out that the multimodality in gravitational waves arises from the fact that detectors cannot distinguish very well signals coming from above or from below. They can also not distinguish very well right from left polarization because they only see a projection. I just said an orbit shift but by pi is a symmetry of the quadrupole moment, so it's also hard to measure. And if you shift the orbit by pi over 2, but also the polarization by pi over 2, the gravitational wave flips signs, but the response of the detector also flips signs, and then it's also another symmetry. So these 4 symmetries give you in general 16 modes of the posterior, which appear is hard to do, but we can use to our advantage that we know exactly these symmetries and how can we use this to our advantage. So yeah.
If you have the one that cannot detect well from above than from below, is it for just one detector? But if you have 2, then it gets this degeneracy or?
Yes, so this is not exact symmetries. And if you have 2 detectors, in principle, we can break it. But the problem is that the 2 most sensitive detectors we have are the 2 LIGO ones that are both in the United States, and they have very similar orientation. So basically, the symmetry approximately remains. Yeah, here I'm showing, for example, 4 events, and you see that for 3 of them, these symmetries indeed happen, and they have all the 4 solutions. But for one of them, it doesn't. The symmetry is broken. This one is special because, first of all, it has 3 detectors, so they break some of its degeneracies. It's also very loud, so you measure things better, and it has this higher order modes of radiations because the masses are unequal. And this again breaks the symmetries of a quadrupole moment. It has higher moments that you can measure. Any other questions? So okay, how can we deal with these symmetries that on so we know where they are, but on the other hand they are not exact. And the way of removing this multimodality is as follows. So here we have one event. I just painted the 4 modes here in different colors. And by choosing your coordinates carefully, you can make it so that they are just reflections. And then you can basically fold the distribution on top of each other, and you land with all the islands in the same place. And now the distribution becomes unimodal. So now you train the normalizing flow to predict this one. And it should hopefully be easier to describe. But still, you're interested in the original one. Remember, the symmetry is not exact, so you cannot just undo it. Or rather, to undo it, you need to train a classifier, and we do this. A classifier that, given the data and the value of the folded parameter, predicts where it should go.
What is the order of your domain? Usually, if you speed borders, it causes problems in the inverse mode. So there's a symmetry better if you just get it to the center.
Right. So this is something I'll touch on later. Maybe I won't, but it's something we do later. That is, once you have this space, now you can still do transformations such as sending the boundaries to infinity, and then this will become more like a Gaussian rather than a truncated thing. But we first do this folding in these specific coordinates that we chose, so that reflections just send the modes on top of each other, and after that, this folded posterior, you can still rescale it. And this is the next. It will come up in a few slides. So okay, after doing all these tricks, remember reparametrizing so that the degeneracy, the bananas are gone, and then folding so that they fall on top of each other. We turn this posterior like this onto this posterior like this, which is much simpler to infer. It's unimodal and looks like a Gaussian more or less. Okay, so here on the left, I'm showing physical parameters like the masses and the sky location. These are things that we're interested in inferring. And how do they look in these new coordinates I just explained? Like on the right-hand side. And you see they look like more or less unimodal Gaussians, which is great. But still, every event falls in a different place. So they are not invariant to parameters of the signal, which is something that we might like to have. So the solution is, so basically a bit from analytic methods, we can go so far, and after that we can put a small neural network that predicts the mean and the covariance matrix of this Gaussian, and we can use this mean and covariance to rescale the parameters in this way, so that all the different events fall more or less on top of each other and have like zero mean and univariance. So again, this is not exact. So you see, it's not quite Gaussian, for example, in this panel, but it's much better. And you can think of this as basically constructing a normalizing flow by hand. If you know, a normalizing flow maps a Gaussian or a simple distribution to the posterior. But now we have to use the actual normalizing flow to infer this distribution, which is almost a Gaussian. The normalizing flow has little work left to do. And as a result, we can train the model much faster than other methods. This is an example injection compared to, say, Monte Carlo. And the answer is fairly similar, but with this simulation-based inference, it's like 1,000 times faster. It gets done in second time scale instead of hour time scale. You have a video on time? Yeah. Okay. Perfect. I mentioned a bit this possible application to detection. So this is an idea for the future, but I just wanted to suggest. So how do we search for these signals? We basically have a detection pipeline which takes data in and needs to rank it compared to other data and compute the force alarm probability of getting a particular instantiation of data. Or rather, the force alarm probability of getting a value of this detection statistic. So at the end of the day, what the pipeline needs to do is compute the detection statistic, which is a function of the data. And there's a theorem named Amperson's lemma that says that the optimal detection statistic is the likelihood ratio between the signal hypothesis, in our case, there is a gravitational wave in the data, and the noise hypothesis that there is not. Yeah, but the problem is that now we have to actually compute this quantity, and the probability of the data given the signal, since the signal can have any parameters, it's an integral over all the possible parameters it will have. So this is the prior for the parameters and the likelihood. And so current pipelines have techniques in place to compute this quantity, but mostly this is more or less a solved problem for simple signals like aligned spins and circular orbits. And this basically these are simple signals that their morphology is simple and allows you to do a lot of approximations and tricks due to this. So it turns out it's very hard to relax those assumptions because many of the tricks that you use cannot be used anymore. And also just the dimensionality of this integral increases. So the main barrier towards including these extra effects that are very interesting to look for is computing this integral. Here, one idea could be using the fact that, for example, normalizing flow is a really powerful description of a distribution because so the typical one that you may want is generate samples fast, and you can do that, but you can also evaluate the density, and the density is normalized. So what this lets you do is to compute this integral, which you can think of the normalizing constant of the posterior by evaluating this unnormalized posterior and dividing it by the normalized posterior. And this should give you this thing that you are interested in for computing the optimal detection statistic. And in principle, with even a single one, it should be correct, a single evaluation of a posterior. If the model is perfect, in practice, probably it's not, so you might want to do a few, but it's a straightforward way, possibly, to evaluate this thing that is the main roadblock towards including new effects in the signal. So I want to conclude with one example of that we recently were able to include some of the these extra effects. I mentioned in passing in the past the gravitational waves mainly emit from the quadrupole moment of the source, the quadrupole mass moment, but it has higher moments, and then those are like extra harmonics of the signal. And we were recently able to implement this likelihood marginalization, accounting for these higher modes. This result in an improved sensitivity. So this is the sensitive volume that we have for a set that includes higher modes versus the 2-2 or the quadruple mode only. And we see that depending on the parameters of the signal, so especially for unequal masses that have higher emission of these extra moments, because the quadruple is not relatively that important, we can get volume improvements over a factor of 2. And indeed, we have detected additional events in the public LIGO data at extending the reach of these detectors to especially higher masses and in distance as well. So yeah, to conclude, by implementing this domain specific knowledge and equivariances in the representation of the gravitational wave data and parameters, our code that is called Labrador because it's easy to train is interpretable. So all these group parameters I mentioned, we know exactly what they are, and they contain most of the information. But we also allow for generic departures, and we let the black box aspect of the machine learning flexibility to capture those generic departures. So it's a good method towards including generic effects. For this reason, it's also exact. The neural network retains the flexibility to describe signals beyond the reference model, and it's very fast. So it trains overnight and can produce posteriors in seconds, which is much faster than the classic methods. So yeah, we have this article and code implementing all this coming soon. So if you're interested, stay tuned for years. We are still in a kind of almost basic phase where we still have to include other effects such as the power spectral density of the detector noise, effects like misaligned spins and higher modes. But in the future, this method is promising for applications for search including these extra effects. So with that, thank you very much.
All right, great talk. Thank you so much, Javier. Any questions? Okay.
So just for general understanding, if I follow your talk correctly, you're saying that there are some symmetries either in the observed system or in the system plus detector that result in some degeneracy in the signal that in turn result in things like multimodalities in the posterior. And you are saying that you can incorporate those equivariances in the model, in the whatever system of neural networks you have to solve this. But it was, for example, here, this is what I wanted to ask. So can you tell us a little bit about how exactly you incorporate, for example, this folding into the architecture of the solver? How is that equivariance actually coded in the neural net?
Yes. So typically, exact equivariances are often baked in the architecture of the network. These ones are not exact, so we cannot do that. So instead, what we do is transform the data to respect these equivariances. And so here, I said at the beginning, to train the system, the ingredients you need are simulations where you know the true parameters and the data. And the idea is that some reflections of the true parameters leave almost the same data. So what we do is just train the model on the folded parameters. So we first fold these parameters by hand in the training set. And we say, okay, this is the data and this is a folded parameter. Please give me the value of the folded parameter. So this is what you're asking the normalizing flow to output. And then you have a different module that, given value of the folded parameters, predicts the probability of the source coming actually from each of these islands. So that's a standard classifier we use XGBoost for this task.
So that's sort of an alternative to do something like data augmentation, where you know, sort of produce more data that would have the same parameters, but then you give the proper label to it so that. I mean, it's not exactly the same as data augmentation, but you manually sort of manipulate the training data in advance and then have a new target for normalizing.
Yes, data augmentation here is hard because since the symmetry is not exact, you need to run the simulation again if you want to simulate this guy and this guy and this guy. So it will give almost the same data, but not quite. So if you want to do it properly, you need to run all the simulations, and the cost is just the higher.
And just a quick follow-up, in the case of, when you say an exact equivariance, would you say that something like the translation invariance in a convolutional neural network, would that be an exact invariance for which you don't need to manipulate the training data, or is that still an approximation?
Yeah, so for example, I think that that's in fact maybe the only one that is exact here, that if you change the overall time of arrival of the signal, you move the data, then the posterior and the parameters move in the same way. So that's an exact one, but I think it's the only one. For example, if you change the sky location, the time of arrival at each detector changes, but also the response of the detector, and this causes some extra changes in the amplitude, so it's not quite exact. Or yeah, I think so.
Thank you.
Okay.
So this is very interesting, but I'd like to come back to the question of the simulation. So it turns out something very similar. The data is normalized and flows. The inference is the power place there, the vector state of probability, and in every single application, there is a mismatch between our synthetic training data and reality. And so I was wondering how you address this issue, whether you have thought about using transfer learning. You could have a layer of transfer put in front of your data to essentially do a transformation in some executed space before you put it to your main machine. So I was wondering how you do this problem. Maybe it's not an important.
Can we repeat the question for the Zoom? I'm gonna do a summary, or you want to? Yeah, because the Zoom will probably not hear you. You're talking about how to close the gap between model and data, and if you can use transfer learning from that for that?
Yes.
Okay.
So is the question if your model is not sufficiently well trained or not sufficient?
No, your INN or your neural network is superbly trained, and as long as you are within the world of the training data, it has fantastic inferences. However, often there's a mismatch between your training data and simulation-based inference and real data. And so I was wondering how
Model specifically, like the same thing that you and Rafael were discussing earlier. If your model doesn't exactly represent reality.
yes, if the model covers this space in parameters and reality is this, you only have partial overlap, and sometimes it is extrapolate.
Okay, so if it's outside the range of the training, or rather, so yeah, in that case, so for example, if the some other thing that has been done among these lens is a sequential neural posterior estimation, where you what I describe as opposed to amortized neural posterior estimation, which is what I described here. So amortized is you train once at the beginning and then you never train again. But imagine now you have an observation and you see that you get a solution that is approximately good but not quite. You can use this to generate more simulations in that region, and then retrain and improve your answer.
You are doing this?
So I myself am not doing this because so the problem with this is that you need to do this step after seeing the data, so it stops being amortized. So that's part of the attractive that we have, but of course you can get better accuracy, and yeah, there is a lot of literature.
And also, this is not my field, but I think from what I know, the expected shape of the signal is very close to what we really observe, right? So the model specification, is it true that in gravitational waves is not too bad? Because it's pure GR?
Yeah, so yeah, I mentioned, I think compared to other astrophysical systems, so the system is just black holes in pure GR. Gravitational waves don't interact with anything, there's no dust, nothing that affects it. They get to the detector, it's just a simple geometrical projection. Of course,
But if it's neutron stars, you have the equation of state, you have internal degrees of freedom, you have
yeah,
additional complication.
yeah, that is very good. And also sometimes the behavior of the detector is not quite what we put in there, so we usually put Gaussian noise, but these detectors have sometimes glitches and so on. And then simulation-based inference is still unexplored, I would say, but a promising way of dealing with this, because you can just learn from the empirical noise of the detector, rather than having to assume a model for it.
Any other questions? I particularly encourage students, if you have any questions, comments, all questions are welcome. Anyone on Zoom? Well, non-students also speak up then. Yeah, go ahead, Olive. Come closer so they hear you soon, please.
Thank you very much for the great talk. I have a question about the spin distribution that comes out of these gravitational wave measurements. I think you talked about it a little bit. I'm not sure if I apologize if I missed it. The chirp map, well, the spin distribution peaks at low spin from the gravitational wave measurements. And there are other measurements like X-ray reflection spectroscopy where we find a different spin distribution. Can you say something about like the level of systematics that are like that you suffer from in your tool or in general with these measurements that impact these distributions?
Yeah, great. So indeed, we have few outliers, but most of the observations, I would say 60–70% are indeed those spins. In general, my understanding is that the systematics in the gravitational wave measurement tend to be small because of this thing we were saying. It's just GR, we understand this very well. This some regimes like an extremely high and negative spins can cause complicated orbital evolution, and this is not necessarily captured by the simple or the fast approximate models that we like to use. So in some corners of parameter space, maybe there are some systematics left, but I think near low spins, this is very well understood, and the measurements should be reliable. Maybe let me add another asterisk there that on the other hand, we cannot measure very well all the components of the spin. So we can mainly measure one called the chi-effective or effective spin, which is an average of the aligned components of the spins of the black hole. Aligned meaning aligned with the orbit. So this basically has a strong effect on the signal, and then we can measure it. But there are other effects that are more subtle. For example, okay, given the same average, how much you allocate to the primary or the secondary, not measured at all. The misalignment angle, very hard to measure. Most events not measured at all. And so there are some things we can say kind of for sure, and some things that are very prior dependent.
Thank you.
Any other questions for Javier? On Zoom? Anyone? Okay, then let's thank Javier again. And hopefully there's still a second.